Okay, chapter 4. This is the most challenging of all the chapters that we'll see in this course, and so much so that your next exam number 2, will just include this chapter 4. There are 3 sections: 4.1, 4.2, and 4.3. So I know I assigned watching this video earlier last Thursday, so you may need to watch it again. It's a challenging chapter. All right, so we start out with a definition. What is probability? I like this definition. Science of uncertainty. It's a number. Probability is a number that represents the likelihood of an occurrence of an event whose outcome is unknown. Probability. Science of uncertainty. In the video, Big Al, as I call him, started out with some basic definitions. An experiment, an example of experiment would be rolling a die, or drawing a card out of a deck of cards, or pulling a marble out of a bag of marbles. The experiment could be a woman having 3 children. Are they all boys, 2 boys, 2 girls? Experiments. The outcome of an experiment is the results. For instance, if you're rolling a single die, your results could be a 1, a 2, a 3, a 4, a 5, or a 6. I'm thinking about a standard 6-sided die. So the sample space would consist of those outcomes. An event of this experiment could be maybe asked to find a probability of rolling an even number or an odd number or a number that's bigger than or equal to 3. These are all examples of happenings. All right. Experiment is a happening whose result is unknown. An event is some subset of the sample space, drawing an even or an odd number, a number bigger than 5, whatever. All right, basic definitions. Now, here's the deal. When we use probability, we're using a number. Well, guess what? This number is between 0 and 1. All right, probability can't be bigger than 1, and it can't be a negative number. It's between 0 and 1 inclusive. That indicates the likelihood of an event. All right, the closer the probability is to 1, the more certain it is to happen. The closer it is to 0, the chances aren't all that great. Probability is a numerical measure between 0 and 1 that describes the likelihood of an event will occur. Probabilities closer to 1 indicate it's more likely to occur. Probabilities closer to 0 indicate that it's less likely to occur. You'll hear me say this here. This P followed by an A in parentheses is read P of A. It denotes the probability of an event A. If P of A is 1, the event is certain to happen. If P of A is 0, that event cannot occur. All right. Most probabilities range between 0 and 1. Can't be bigger than 1. It can't be a negative. Can't be less than 0. 3 ways of calculating probabilities. The first one I can't very well test you on. It's probability assigned based upon intuition. We often hear about women's intuition. All right. Intuition incorporates past experience, judgments, or an opinion to estimate the likelihood of an event. What's the probability that Major League Baseball resumes and the Red Sox win the World Series? All right. That's based upon your own judgment. So I can't very well test you on intuition because each person has their own intuition. However, on the next two, all right, ways of finding probability. One is based upon what's called relative frequencies. How many times did something happen, and how many times were the observations made? Um, for instance, I could say intuition. It's Tuesday, and my wife normally makes spaghetti on Tuesday, so I think the probability that she's making spaghetti this Tuesday is maybe zero point 0.7 or zero point 0.8. All right, based upon the frequency of an event in a sample space. How often does it happen in the past? And how often did I observe these outcomes? And we'll have some examples of this. A major way that we're going to calculate probability, especially, well, throughout the textbook in chapter 4, and specifically in section 4.1, we're going to base it upon equally likely outcomes. All right, the number of favorable outcomes over the total number of outcomes. For instance, drawing a card out of a deck, what's the probability that I draw out a club? Well, Total number of outcomes is 52 cards in a regular deck. 13 of those cards are clubs. So the probability of me picking a club at random would be favorable 13 out of a total of 52. We'll see many, many examples of this as we move forward. So three ways, and basically the relative frequency and equally likely outcomes are the only two things that should be tested on, because can't test you on intuition. Everybody has a different intuition. All right. Now, over the years, I've come to the conclusion, obviously, that not everyone, and not everybody's family played cards at home. All right. I found a lot of students where certain foreign countries they were not allowed to play cards. So, going on that assumption, I actually give you a standard deck of cards. There's four suits: clubs, spades, hearts, and diamonds. All right. And what I want you to see is many times we want to consider face cards. All right. Now, I know in some decks the ace has a face on it, but in this deck, we're talking probability in this course. We don't consider the ace to be a face card. Face cards are the jack, the queen, and the king. Now, obviously, there's three face cards in diamonds, three in hearts, three in spades, and three in clubs. So a total of 12 face cards. So if I'm asking you what's the probability that I randomly pick a face card out of a standard deck, favorable would be 12. Total cards in the deck, 52. 12 over 52, the lowest terms. Many times we talk about rolling a die or sometimes a pair of dice. All right, single die has six sides: one, two, three, four, five, six. And I know in some board games you have an eight-sided die. I'm talking about a standard die, six-sided. All right, and here again, sometimes we're not rolling a single die; we're rolling a pair of die. All right, so you see, for instance, here, how many ways can I roll a four? Well, I can get a one on the first die, a three on the second, a two, two, or a three, one. There are three different ways of me rolling a four. Well, favor would be three. There are a total of 36 different combinations. So the probability of rolling a four would be favorable. These three out of 36, lowest terms 112. I suggest strongly that you have this in your notes and you're going to make use of it come test time. So that's the dice and also the previous one, the playing cards. All right, four suits. Can't go on the assumption everybody knows that there's 52 cards and there's four suits. So please print this out, have it with you. The outcomes of a sample space are called equally likely if all of them have the same chance of occurrence. Toss some coins or a coin. When the coin is tossed, it has two possible outcomes called heads and tails. We shall assume that head and tails are equally likely if not otherwise mentioned. You've heard the term loaded dice roll. We're not talking about loaded dice or loaded coins. We're talking about, hey, heads and tails here being equally likely. And number two is throwing dice. We throw a single die. There are six possible outcomes: one, two, three, four, five, six. Now we're going on the assumption that this is a fair die. Each side has the same probability of popping up. Let's say the probability of me rolling a four on a single die. It was only one four. There are a total of six different outcomes, probably of rolling a four, favorable one, total six, one chance of six. We do a lot with playing cards. I just mentioned this in a previous slide. 52 cards in a regular deck. Jack, Queen, and King being the face cards. Marbles in the bag, many situations and probability in which some objects are selected from a certain container. The objects of the container are assumed to be equally likely. All right, a famous example is a selection of a few marbles from a bag containing balls of different colors. All right, maybe ask, hey, what's the probability of me drawing a blue marble or a red marble? We'll see some problems like that. Things that are not equally likely. Well, if I were to drop this box of matches, chances are I would land on the larger edge as opposed to landing on one of the small edges. Dropping a tack on a floor, chances are it's going to land this way as opposed to landing with this larger surface on the bottom. Um, Drawing marbles from bags, but now I'm talking about different sized marbles. And if you have different sized marbles, if you put your hand in the bag, you're more apt to draw the one that's larger than one that's a little tinier. Weather. You wake up in the morning, you don't say, well, chance of it raining is 50-50. Either it rains or it doesn't rain. No. Meteorologists, fly balloons and they'll come up with a probability. Tuesday, probability that it rains is 10% or 20%. Right? And they use all sorts of some science, actually. You can read this over here about the National Weather Service and how they float balloons into the atmosphere and collect wind speed, direction, temperature, and they come up with a probability that's going to, rain, or if it's winter time, probably it's going to snow, so on and so forth. All right, things are not equally likely. Raining and not raining on a particular day is not 50-50. Consider each of these following events and determine how probability was assigned. The sports announcer claims that Sheila has a 90% chance of breaking the world record on the dash. Well, perhaps the sports announcer has been following Sheila's last 4 or 5 different track meets, and he noticed that her times are getting, each meet they're getting better and better. So the sports announcer says that today's the day that Sheila is gonna, break the record. Perfect conditions. It's no wind. The track is fast, and all right. So what we're doing is she's basing this on intuition. She's not basing on equally likely or frequency or relative frequency. She's just, hey, I think she's going to break the record based upon her times getting better and better. All right, intuition. Henry figures that if he guesses on a true-false question, his probability of getting it right is 0.501 half. Key word here is guessing. You're taking an exam, all right, true false test, and you studied hours and hours. Well, your probability is not 50-50. Your probability should be closer to 1. Should else be a sure thing if you put the time and effort in. All right, so in guessing, it's 50-50. It's a true false question on a subject he hasn't studied, has no idea of. He's just going to guess. All right, so it's a 50-50. Be aware if you've studied, obviously, your probability of getting it right should be a heck of a lot better than 50-50. Getting back to Henry's problem, there are 2 possible outcomes. Henry is either correct or incorrect. Since Henry is guessing, we assume the outcomes are equally likely. Possible outcomes, there are 2 equally likely outcomes, and only one of them is correct. So favorable over total probability of getting a true false question right is 1/2. And here is that 1/2 is expressed as a decimal 0.50. A random sample of 500 students at Hudson College was surveyed. It was determined that 375 wear glasses or contact lenses. Estimate the probability that a Hudson College student selected at random wears corrective lenses. Well, relative frequency. These wearing glasses and not wearing glasses aren't equally likely. So we're basing our answer on past experience. We've surveyed 500 students, and out of those 500, 375 wore glasses. So the probability that I select somebody at random who wears corrective lenses glasses would be 375 over 500. All right, favorable over total. All right. Well, I shouldn't say even favorable. I should say frequency over total. Basically, this here, relative frequency and equally likely, is still forming a fraction. So in certain instances, or certain cases, it's the same way in solving it. You're putting it favorable over total. In this case, 375 over 5. Friends of the Library host a fundraising barbecue. George is on a cleanup committee. There are 4 other members on this committee. There are 4 total members. And they draw lots to see who gets to clean the grills. Assuming that each member is equally likely to be drawn, what's the probability that George will be assigned a grill cleaning job? Well, favorable. George may not think it's favorable, but George is only one person, and there's a total of 4 people. Probability he gets picked is 1 chance in 4, 0.25. Joanna photographs whales for Sea Life Adventure Films. On her next expedition, she is to film blue whales feeding. Based upon her knowledge of the habits of blue whales, she is almost certain that she'll be successful. All right, so she's using intuition. All right, says what specific number do you suppose that she would estimate the probability? Well, if she's pretty certain she's going to see some blue whales, she's probably going to maybe put the probability close to 1, like 0.9, 0.90. Many of you have gone on whale watches, either in Plymouth or maybe Provincetown, and we get on board the ship. The tour guide says, "Hey, I've been seeing whales all week. I'm pretty sure we're going to see some whales today. I'm going to put the probability at 0.85. Maybe if she hasn't seen a whale in months, she may say, hey, the probability we're going to see a whale today maybe is 0.2 or 0.1. At that point in time, you probably would ask for your money back. Gender of children. All right, we do a lot with women having children, right? And we're looking for the combination of, hey, two boys, two girls. Was a first child a boy or girl, and so forth. So this would be very helpful, this list right here. All right. There are 8 different outcomes when a woman has 3 children. All right. The first child could be either a male or female, so 2 possible outcomes. The second child could be a male or a female, 2 possible outcomes. The third child, here again, male or female, 2 times 2 times 2 for a total of 8. The sample space consists of 8 equally likely outcomes. And I say equally likely, we assume, I know in scientifically, I think right now, boys are maybe 0.52. It's more boys are being born, but we're going to assume that a woman having a boy or a girl, it's an equally likely situation. Of course, I'm not considering where they're taking any sort of kind of fertilization drugs and people picking, parents picking the gender of the child. I'm not talking about that. I'm just saying 50-50, like tossing a coin, right, boy or girl. Now, there are 8 different ways. So what we're asking is find a probability of having a couple has 3 children. They'll have exactly 2 boys. Well, the first 2 children could be boys, or maybe the first and the third. And then the last choice would be the first child is a girl, and the second and third child are boys. So favorable, there's 3 different ways that you can get exactly 2 boys out of a total of 8. That's very important. Sample space consists of 8 different outcomes. 2 times 2 times 2. And they've changed, in this case, they changed 3/8 to a decimal point 375. The technique of using relative frequency of an event as the probability of the event is a common way of assigning probabilities and will be used a great deal in later chapters. The underlying assumption we make is that if the events occurred a certain percentage of times in the past, they will occur the same percentage of times in the future. In fact, this assumption can be strengthened by what's called the law of large numbers. The law of large numbers says in the long run, as the sample size increases and increases, the relative frequency of outcomes get closer and closer to a theoretical or an actual probability. For instance, let's say you're tossing a coin 10 times. All right. You say, well, how many times did I get a heads? How many times did I get a tails? No, it's not going to be 50, 55 heads and 5 tails. You may toss a coin 10 times and 8 of those tosses are heads, or maybe 8 of them are tails, or 7. But the law of large numbers says this: if I toss a coin, let's say 10,000 times, and I recorded the number of heads and the number of tails, it's pretty much going to be a 50-50 situation. Number of heads would be 5,000, pretty close to that, and the number of tails would be 5,000. The more you do something, right, you repeat an experiment, the closer the results get to the true probability. This is why insurance companies never lose money, right? Automobile insurance. They know that people under a certain age are more apt to get into accidents than people, let's say, of an older age. So that's why younger people get charged more for insurance. Casinos, the odds are always in favor of the casino, right? So if you stay there long enough, guess what? You're going to lose some money because the odds are in their favor, all right? No matter how we compute probabilities, it's useful to know what outcomes are possible. You may want to check out this dice simulator. You can roll a die on multiple times, thousands of times, and you'll see, say, rolling a die that if you rolled it 10,000 times, the numbers of ones and twos and threes and fours would even out. They would be about the same because the law of large numbers says this. The more and more I do something, the closer the results are to the true probability. Probably of rolling a 5, let's say, is 1 chance out of 6. You could roll a die, let's say, 20 times and maybe get, 7 times you got a 1 and 3 times you got a. If I did it a lot of times, it would even out. The number of times you get a 1, a 2, a 3, a 4, and a 5, and 6 would be about the same. The sum, this is really, really important. It's a small point, but it's huge. The sum of the probabilities of all the simple events in the sample space must equal 1. Probability of rolling a 1 is 1/6, a 2 1/6, a 3 1/6, a 4 1/6, a 5 1/6, a 6 1/6. You add up all those probabilities, 1/6, you add it up 6 times, guess what? You get 1. Something's going to happen. It's guaranteed. We can use this fact to determine the probability that an event will not occur. And many times it's easier to find a probability that it doesn't occur and then calculate the probability that it does occur. You come at it kind of in reverse order. For instance, if you think the probability is 0.65 that you win a tennis match, you can assume that the probability is 0.35 that you'll lose, the opponent will win. How did I get to 0.35? I took 1, subtracted 0.65, and it gave me 0.35. Called a complement. The complement of an event A is the event A does not occur. All right, the complement. Complement of A is the event that A does not occur. And how we signify this is with an A and a bar over it. It's called a complement. All right, complement of A. The complement of A is the event that A does not occur. Now, some textbook use an A with a C. Our textbook uses the A with a bar over it. All right, not this little C. We know this, probably an event happening plus the probability that it doesn't happen has to equal 1. All right. The probability that an event does not occur is equal to 1 minus the probability that the event does occur. Rolling a die, probably of me rolling a 4, 1 chance in 6. There's 6 sides to a die. 4 happens to be one of them. Probability that the 4 does not roll out is 5 chances out of a 6. One of these two things is going to happen. Either you get a 4 or you don't get a 4. And the sums of the probabilities obviously equal 1. If I know that the probability of an event not occurring is 0.7, I'm sorry, if I know the probability of an event A happening is 0.7, the probability that that doesn't happen is 1 minus 0.7 or 0.3. Maybe a little 2. If I know the probability of an event E happening is 0.15, the probability that it doesn't happen is 1 whole minus 0.15 or 0.85. The sums of the probabilities have to equal 1. This is just a little bit of an algebra here, right? If I'm solving for the probability of A, I'm going to subtract the probability of the complement on both sides. You can also use this if I want to know the probability of something not occurring. It's 1 minus the probability that it does occur. Very powerful here. Very powerful. We're going to talk about the complement rule in greater detail. And we're going to have a series of problems. We're going to be computing the probability of at least one success. The probability of at least one would be 1 or 2 or 3 or 4, up to how many times you're conducting the experiment. All right, we're going to make a wide use of the complement rule. The problems fall under the category probability of at least 1. We'll talk about that probably next video. The complement of at least 1 is none. The complement of at least one event happening is that the event never happens. All right, consider the experiment of tossing a fair coin 3 times. For each coin, the possible outcomes are heads and tails. List the equally likely events of the sample space. What's the probability that all 3 coins come up heads? All right, this is very similar to a woman having 3 children. Instead of having heads and tails, we're saying boy and girl. All right, so this is a sample space. All right, for tossing a coin 3 times. Heads, 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 tails, heads, tails, heads, heads, tails, tails. What I would suggest is, start off with all the ways that you can get a heads to start off with. And there are 4. Once you have everything here with a head starting off, in place of an H, replace the H's with T's. You'll notice that the sample space consists of 8 items. Event A can happen in 2 ways. Event B can happen in 2 ways. And event C can happen in 2 ways. 2 times 2 times 2 is 8. So what's the probability of getting heads, heads, heads? Well, there's one favorable outcome out of a total of 8. So that's one way of doing it, 1 chance in 8. And what's the probability of at least one tail? Well, 1 minus the complement of all heads means you get at least one tail. All right. So 1 minus probability of all heads would be 1 minus 1/8 or 7/8. But notice I can say there's one tail here, one tail, at least one tail here, at least one. Two is at least one tail there. Sometimes using the complement rule is a faster way of getting to your result rather than counting them individually. Probably of a college student who has not received a flu shot gets the flu is 0.45. What's the probability that a college student will not get the flu? Well, in this case here, probability of getting the flu is 0.45. The probability of not getting the flu is 1 minus the probability of getting the flu. All right, 1 minus 0.45 is 0.55. Right? Either you're going to get the flu or you don't get the flu. Two things. And the sum of those probabilities equals 1. So if I know the probability of getting the flu is 0.5, probability of not getting it is 1 minus 0.45. Suppose a newspaper states the probability of rain is 30%. What's the complement of rain today? Well, it doesn't rain. What does that mean? It's cloudy, it's semi-cloudy, who knows? All right. What's the probability of that complement? Well, 1 minus 30%. Well, 30% is a decimal, is 0.30. 1 minus 0.30 is 0.70. Here it is. Complement of rain today means it didn't rain. What does that mean? It could be anything. Cloudy, not cloudy. It could mean snow for that matter. Right? All I know is it's probably that it won't rain is 1 minus the probability that it does rain, 0.7 or 70%. What is the law of large numbers? If you're using relative frequency of an event to estimate the probability of the event, would it be better to use 100 trials or 500? Well, obviously 500. Better still to use 1,000 and 500. The more trials, the closer that probability will get to the actual probability. Right? Law of large numbers. The more and more times you do something, the closer it gets to the true probability. What's the probability that the day of the week selected at random will be a Wednesday? Well, all the days of the week are equally likely. They all have 24 hours. There's 7 days in a week. Wednesday happens to be one of those days. Favorable is 1. Total is 7. Probability is 1 chance in 7. Now, this next one suckers people in, all right? And what's the probability that a student in our class chosen at random was born in the month of November? When you first start as well, it's 12 months in the year, and November is one of those months, so the probability of a person selected at random being born in November is 1 chance in 12. Well, wrong. The reason it's wrong is these days in a month are not equally likely. Some months have 30 days, some have 31, and February has 28. All right, so you can't use, they're not equally likely, so you can't say 1 chance in 12. What you can say, all right, there are 365 days in a year. I'm not considering leap year. And the month November, 30 days has September, April, June, and November. November has 30 days. Probability of a person selected at random being born in November is 30 out of 365. It's not 1 out of 12 because the months are not equally likely. Some months have more days and some months have less days, and February only has 28. So it's not the same way of calculating as you did in the previous example with days of the week. All days have 24 hours. All months don't have the same amount of days. You're more likely to be born in a month with 31 days than you are in a month that has only 30 days. Sample space consists of 4 simple events, A, B, C, and D. Which events comprise the complement of A? Well, things that are not A are B, C, and D. Can the sample space be used? Can the sample space be viewed as having 2 events? Yeah, A and the complement of A. Right. This here is couples, 375 randomly selected couples, and this lists the number of similar preferences they have. All right, uh, 34 couples had all 4 um, similarities that they agreed on. 131 couples agreed on 3 things, and then you had 15 couples that didn't agree on anything. And you wonder why they got married. Use the data to estimate the probability that they have 0, 1, 2, 3, or 4. Well, the probability that you pick a random couple and they have all 4 similarities would be favorable would be 34. Frequency would be 34 out of a total of 375. 34 over 375. For 3 similar traits, it'd be 131 over 375. 2 would be 124 out of 375. Not saying they're equally likely, but I'm basing upon past experience. It happened a certain percentage of time in the past, it'll happen the same percentage of times in the future. All right, odds against. Betting odds are usually stated as against the event happening. Here again, I make sure that I would copy this formula down. The odds against something happening is the probability that it doesn't happen over the probability that it does happen. This is going to be a fraction and that's going to be a fraction. They'll both be decimals. Make sure you've got this form. It's easy enough. Odds against something happening is the probability. It's a ratio of the probability of it not happening over the probability that it does happen. All right. You bet you can roll the number that you pick in advance when rolling a single die. You pick a number from 1 to 6, then you roll the die. If your number comes up, you win. Otherwise, you lose. What is a fair payoff? Well, probability. All right. The probability of picking your number correctly when you roll a die is 1 chance in 6. You pick a number, there are 6 possible numbers that can come out: the 1, the 2, the 3, the 4, the 5, and the 6. Say you pick a 4. You have a 1 in 6 chance of the die coming out 4. What's the complement of that? Well, there's only one number that's favorable to you. There are 5 that are not favorable. All right, so probably that you don't win is you have 5 chances of not picking the right number over a total of 6. So if you're looking for the odds against, it's the probability of the event does not happen over the probability that it does happen. All right. Now, when you do this back in grade school, you're taught that division. To solve a division problem with fractions, you change the division sign to a times sign and you multiply by the reciprocal. Reciprocal of 1 over 6 is 6 over 1. What ends up happening is the sixes cancel out, and your odds against are 5 to 1. For a fair payoff, $5. For a fair payoff, $5 should be paid for every $1 bet. So if you bet $5, your payoff odds against are 5 to 1. You should get paid 5 times 5 or 25. If you bet $10, you should get 5 times 10 back or $50. Roulette wheel has 38 slots. All right, you have one slot that's a 0 and one's a double 0, and the other numbers are numbers from 1 to 36. So you have 36 numbers plus the 0 and the double 0. What's the probability of winning? All right, number of favorable outcomes. You place a bet that the number will be an odd number. Well, how many odd numbers are there? There are 18 of them. We don't consider 0 or double 0 to be odd or even. So if you have 36 regular numbers, 18 of those numbers are odd and 18 are even. All right, so probability of winning would be 18 out of 38, favorable over total. Find the actual odds of winning. How much do you make if you put down $18? Let's go to the next slide here. Here again. The odds against winning is the probability that you don't win over the probability that you do win. Now, since there's 18 odd numbers out of 38, there are 20 numbers that aren't odd. So it's the probability of not winning over the probability of winning. And notice what happens here. The 38s, if you did the division here, 38s would cancel out. You'd have 20 over 18 or 10 to 1. Sorry, 10 to 9, excuse me. If the pay odds are 1 to 1, a winner gets back, you bet $1, you get back $1 for every dollar you bet. If you bet $18, you get your 18 back plus $18 extra. All right, that's $36. Your profit is 18. If the payout odds are 10 to 9, a win gets you back $10 for every $9 you bet. So if you bet $18, you should get your original $18 back. Plus, if you're putting down money on this, you should get your $18 back plus an additional 20. So already we see that casinos don't pay true odds. This is why casinos can't lose. By rights, you should be getting back $20. But the casino in real life is only giving you back $18. The odds are in their favor. They're not paying true odds. If they did pay true odds, casinos wouldn't be in business. This is why if you ever been to a casino and you win something big, they want to keep you there. They'll comp you a room, whatever, because they know the longer you stay there, The odds are in their favor that you're going to lose. The odds are always with the house. Find the odds against correctly answering, getting the answer to a multiple choice question if there's six possible answers. Well, if there's six possible answers, only one of those answers is going to be correct. All right. Only one answer. So if there's six questions, six possible answers, and only one is correct, five of them are wrong. So the odds against is the probability of not getting it right over the probability of getting it right. Well, there's five answers that are wrong out of six. Probably that you don't get it right is five chances in six. Probably if you do getting it right, there's only one answer that's correct. You have a 1 in 6 chance. So the odds against is the probability of not winning over the probability of winning. So this is 5-6. Probability of winning is 1-6. Here again, when I multiply by the reciprocal, the sixes cancel out, and my odds against winning are 5-1. In fact, $5 for every dollar I win. All right, not that we're going to, go to a casino, but a lot of problems we deal with do have to do with gambling and drawing cards and rolling dice and things of that nature. So you may need to. The test is the next test we're going to have, which will be probably in a couple of weeks, and I'll give you much advance notice on that. But you may need to watch this video more than once. When I assign the practice sheets, I'll obviously go through it in detail. But feel free. I mean, I haven't seen many questions in the discussion board. I've been looking. People have been doing a decent job logging in. There's a few folks that. What I'm trying to say is I can see behind the curtain. I can see the last time you logged in, and it also gives me a total of how many minutes or hours that you've been on Canvas. Now, you're not logging into Canvas, watching these videos, downloading these assignments. It's setting us up for failure. And to be honest, I can see. And I haven't emailed anybody specifically, but I know who's logging in and how much time you're spending. So, alrighty.